Hi everyone, my name is RVS Harshni. I am studying in Venkateshwara College of Engineering, Bangalore. So today I am here to discuss about physics. So let us go about. The main topic of today's video is Lorentz field and Clausius mossotti equation. So the contents that we are discussing today in the today video is Lorentz field, internal field in solids, that is also called as the Lorentz field, and what is the use of Lorentz field, what is the Lorentz field, what is Clausius mossotti equation, what is the derivation of that equation, and what is the use of this equation, everything in detail. So let us discuss our first topic, that is Lorentz field. So Lorentz field. The figure shows a small experiment by which we can easily understand what is the specific certain meaning of the Lorentz field. So let a dielectric be placed between the plates of a parallel plate capacitor and let there be an imaginary spherical cavity around the atom A inside the dielectric. It is also assumed that the radius of the cavity is large compared to the radius of the atom. So here, just assume that there are the two parallel plate capacitor and there will be an imaginary spherical cavity around the atom as shown in the figure. So let it be, it is inside in the dielectric. So it is also assumed that the radius of the cavity is large compared to the radius of the atom. So this experiment creates a certain field across the atom A as shown in the figure. This field is called as Lorentz field. Internal field in solids. When dielectric material subjected to an external dipole's electric field, each atom develops a dipole moment and acts as electric dipole. Hence, the field at any given atom will be the resultant of the applied electric field and the electric field due to the surrounding dipoles. So, the internal field in the electric field that acts at the site of any atom of a solid subjected to an external electric field and is the resultant of the applied field and the field due to all the surrounding dipoles. In one dimension, the internal field is given by EI equal to E applied plus E dipoles. So we can simply say that the solid's internal field is EI equal to applied electric field plus the electric field that is developed across the dipoles. In three-dimensional case, EI equal to E plus gamma by epsilon naught into P. So here the terms that is shown in this equation is gamma is the internal field constant, P is the polarization, and epsilon naught is the permittivity of the free space. So for 3D, the internal field is called Lorentz field and it is given by E Lorentz equal to E plus P by 3 epsilon naught. So the internal field that is situated in the any 3D dimensional phase is Lorentz field. So here the gamma equal to 1 by 3 if the lattice is the cubic lattice. So make sure that, and please be aware that gamma equal to 1 by 3 for any and for every Lorentz field. So this gamma equal to 1 by 3 equation is useful to solve the numericals and certain things where you can know the Lorentz field and the gamma value that is equal to 1 by 3. So the above equation is called as the Lorentz relation. So the applications of the Lorentz field. The applications of Lorentz codes are defined as follows. It is used in the medical industry in the form of an instrument known as hydrophone. It is used as ultrasound transducer in the medical field. Lorentz force is also used in electrical impedance tomography, which is an imaging technique. Lorentz force also generates shear waves in soft tissues. With this, we completed the topic called Lorentz field. So let us talk about our next topic, Clausius-Mossotti equation. So first of all, what is Clausius-Mossotti equation? Who created it? What is the history of Clausius-Mossotti equation? So the equation provides a link between a microscopic quantity like the polarizability and a macroscopic quantity like the dielectric constant. So this is the link and the relation between the polarizability and dielectric constant. It was derived using macroscopic electrostatics by the Italian physicist Ottaviano Fabrizio Mossotti. His birth date is from 1791 to 1836. In 1850 and independently by Rudolf Clausius in 1879. So, as these Ottaviano Fabrizio Mossotti and Rudolf Clausius has invented this equation, this relation between the polarizability and dielectric constant. This relation and this equation is called as Clausius-Mossotti equation, which is the symbol for their sacrifice, symbol for their invention. It works for best for the gases and is only approximately true for liquids or solids, particularly if the dielectric constant is large. Now, let us discuss about the derivation of Clausius-Mossotti equation. So now, if let us consider the elemental dielectric material in which there are no ions and permanent dipoles, the ionic polarizability of and oriental polarizability alpha naught are zero. So as there are no ions and there are permanent dipoles, the ionic polarizability and oriental polarizability alpha naught equal to zero. So it is given as alpha equal to alpha not equal to 0. Let you assume that it is an equation 1. So we all know that polarization P equal to N alpha E into EI. So from the internal field EI equal to N alpha E into E plus P by 3 epsilon naught. That is P into 1 minus n alpha e by 3 epsilon naught equal to n alpha e. So assume this as the next equation, that is P equal to n alpha e by 1 minus n alpha e by 3 epsilon naught. Assume it as third equation. And we know the another equation, that is D equal to P plus epsilon naught into E. So from that we can know the polarizability P equal to D minus epsilon naught into E. Now, P by E equal to D by E minus epsilon naught. So, where D by E equal to epsilon minus epsilon naught, that equal to epsilon naught epsilon r minus epsilon naught. So, from this, by substituting this equation, P equal to E epsilon naught into epsilon r minus 1. Assume this as the fourth equation. Now substitute 2, 3, 4 in the first equation. So that is given as E equal to E epsilon naught into epsilon r minus 1. That equal to N alpha E by 1 minus N alpha E by 3 epsilon naught. So now 1 minus N alpha E by 3 epsilon naught equal to N alpha E by epsilon naught into epsilon r minus 1. Now 1 equal to N alpha E by 3 epsilon naught into 1 plus 3 by epsilon r minus 1. That is N alpha E by 3 epsilon naught equal to 1 by 1 plus 3 by epsilon r minus 1 plus 1. By taking LCM, epsilon r minus 1 by epsilon r plus 2. So we get the relation between the epsilon r, that is the polarizability, and um, the electric constant. So that is epsilon r minus 1 by epsilon r plus 2, that equal to n alpha e by 3 epsilon r. This is called as Clausius-Mossotti equation, that is derived by them. So that the equation is known as Clausius-Mossotti equation, where n is the number of molecules per unit volume. One can determine the value of polarizability knowing the value of relative permittivity. So the terms that are expressed in the Clausius-Mossotti equation are these. So by dividing the equation, uh, by multiplying the equation with m by rho, it is given as m by rho into n alpha by 3 epsilon naught equal to m by rho into epsilon r minus 1 by epsilon r plus 2, that equal to n alpha by 3 epsilon r, where alpha m is molar polarizability, m is molecular weight, rho is density, Na is Avogadro number. The following are the uses of Clausius-Mossotti equation. So this equation is used in various departments like material science, optics, thermodynamics. So material science, the Clausius-Mossotti equation is used to predict the dielectric properties of materials based on their molecular structure. Optics. The Clausius-Mossotti equation is used to predict the optical properties of materials including refractive index. Thermodynamics. It is used to calculate the heat capacity of materials based on their molecular structure. Thank you for watching my video. Please like, share and subscribe.